I'm going to give a talk today on semiconductors and how they are made in America. And I think that I'm going to try to make the case today that not only the 20th century's greatest engineering marvel, but that it could only have come from America. Real quick, a little bit of background. This is me. I live in Almaty almost 2 years. I was just saying it's the most beautiful place and the kindest people that I've ever lived with. I'm an American. I'm actually an engineer by training, but also I've been an entrepreneur and an investor. I've been in semiconductors for only 4 years. So some of this is new for me, but I've worked in hardware, electronic hardware for 20. And in January, I started this podcast, The Siliconomist. I'll give you the link later, but I love now to have conversations about semiconductors, very passionate about it. You'll see it's a really rich subject. It's really got some great stories with it. Right now, my day job is consulting, work at a semiconductor startup and a few other consulting gigs around semiconductors. So it's also my day job, but I do love talking about this stuff. Yeah, I'm excited to tell you the story and how it uniquely relates to America. I'm not a U.S. government employee, so everything I say here, they're my own opinions. They're the Siliconomist's opinions. So go on my podcast and give me a 1-star review if you don't like what I say. But I have a few slides here to level set and sort of build up my argument about why semiconductors are important and why they could only have come from American culture. But I'll make the case that they're the greatest engineering achievement of the 20th century. They impact almost every portion, every piece of the function you have to do as a government, for example, depends on semiconductors, from feed your people to run your currency to health, education, and defense. These are now viewed as strategic assets to countries, and many countries invest and related to a lot of defense stuff because you can't do these things unless you have some control of your semiconductors and you have some control of the supply. On the other hand, the market also says that they're pretty valuable. Chevron, who are sitting under their large S here, the market values everything that Chevron does in this world at about $500 billion, so $0.4 trillion, which is a lot because I don't have $1 trillion. But NVIDIA is actually priced at more than 10 times that, $4.7 trillion. So you get the sense that, and that's what NVIDIA does all day. All they do is design semiconductors all day. I think the market thinks they're pretty valuable too. So semiconductors are kind of a big deal. I'm going to give a quick background on semiconductors as well, just so you can understand that some of the stories I'm going to tell are a little bit technical. They're based on the technology and the development of the technology. So the fundamental unit of semiconductors is the transistor. You think of it as the basic building block. It's a switch. And when you think about the switch, you've got these two different materials and they're sandwiched together. And sometimes they conduct electrons. Sometimes electrons will flow through them. And if you put them in a different state, sometimes they do not. So that's why they're semiconductors. Sometimes electrons flow through them, sometimes they don't. I found this great analogy. It's a plumbing analogy. If you look at the gate up here, when you put a little pressure on that gate there, you open this valve and water can go from the source to the drain. And it works analogously with electricity. When you put some electricity on the gate, electrons flow from the source to the drain. This is how we diagram it out when we do a diagram of the transistor. That is the very basic building block of semiconductors. So how do we get from a switch, when you think of ones and zeros, how do we get from that to an advanced chip that you find in your phone or your computer? A little bit of magic there, but remember that switch is the ones and the zeros. When switch is on, it's a 1. When it's off, it's a 0. Back to our transistor. When we link a few of those together in a certain way, see that we can start to do what's called Boolean logic. We get a on-off, and that becomes magically basic math functions. And then from there, when we string a few more of them, maybe 1 billion or more together, we start to get more complex processor functions that you think of that you guys would be familiar with when you're doing with Python and C++. So basically we take the transistor, we put it together in different logical ways, the design, and then a few billion of them later, we've got a working microchip. We can all accept that magic real quick. The other piece that I want to just level set on is on size and numbers, because some of the things we're talking about 100 billion transistors. I can't really visualize 100 billion. And as humans, it's just not a scale that we're able to sort of think about. And we're also talking about things that are on the nanometer size. And so a nanometer is 1 e⁹ that's got 9 zeros between the 1 and the meter, if you will. So if I can give a little perspective here. So this video, I'm going to zoom in. If you look at that square there, that's 10 millimeters. And as we zoom in, we're going to go down to the nanometer level. And the nanometer is about the scale that we start talking about transistors. Hopefully this gives you just a sense of how small these are and how many there are. Let me play this. Has anybody seen this video before? Here we go. Okay, so start zooming in. You can see we've got many, many fields. It's almost like we're zooming in on a map. We're going to zoom in on one of these fields here. It's going to look like kind of like one neighborhood. And then as we zoom in, start seeing, because we're going to go down to the electron microscope level, the nanometer. But you see, every time we think we're there, we're just zooming in further and it reveals a whole nother neighborhood until finally we're down to about the nanometer. And you can kind of see right here, you get the sense this is where the transistor is. Like that's maybe the size. So we start out, you think of the millimeter as what you can kind of understand as a human, and we're going pretty deep. Just to give a sense of how miraculous how many these machines are, you kind of understand the size of them. To make the miracle happen, we sort of have 3 ingredients. They've got to be, to get to where we are with phones and with computers, they've got to be small and they've got to be cheap, and they've got to be reliable. And so we're going to take you on the journey of trying to get all 3 of these and the scientific breakthroughs that happened. And I'm going to try to explain that there were more or less, I'm going to break it into 5 big technical hurdles to get from the very beginning of the story to close, the PC revolution, kind of where it begins to be a computer in every house and a computer chip kind of everywhere you go. There were 5 big hurdles. We started out with shoddy logic. Earlier, I was talking a little bit about the vacuum tube, and that's where we started. It's pretty shoddy. And then when we invented the transistor, we went to the tyranny of numbers. I'll explain what that is along the way. We had to miniaturize things very, very small. And then we had to make it very repeatable. And then we had to get all the way to scale, like be able to make a ton of these chips to make them very, very cheap. And what I hope to do is sort of tell the story in a way that shows that this could only have happened in America. And it's not because Americans are smarter, but more so because a great engineering feat is like, it's rooted in culture and reflects the values of the society that produces it. And America has sort of these 5 specific values baked into the culture that made each one of these hurdles possible. So starting with freedom of speech and how that tied into the overcoming the shoddy logic, irreverence, being pragmatic and not dogmatic, running a meritocracy, and then allowing outsiders to come in and participate. And I'll show how each of these are kind of linked to each of these. Real quick, a little bit more background because I love the historical stories. It all starts with Edison, one of the greatest inventors, also an American. And Edison was very practical. When he was inventing the light bulb, he noticed that when you put 2 pieces of metal together, they had electricity would kind of hop between them. He was a very practical guy who was trying to make money. And so he saw this, he named it the Edison effect, and he moved on and didn't really do anything with it because he couldn't make money off of it. Scientists following him after he called it the Edison effect, this led to the discovery of the photoelectric effect, which led to a whole new portion of physics called solid state physics, which more or less talks about materials and then how electrons flow through them. One other thing that Edison did, and many things that he did, he started a lab, but his lab was pretty special because it was the beginning of, he invented the idea of building an institution that would just try to do inventions. So Edison was practical. He put together this lab, but the lab was just for making inventions. He would hire smart people. They would come in and work on problems, but they were problems that were practical and that he could eventually sell with. So fast forward to Alexander Graham Bell. Alexander Graham Bell, born in Scotland, emigrated to Canada, and then came down to America. He was obsessed with helping the deaf. And if you may remember, Alexander Graham Bell invented the telephone. That was an old telephone. And from the telephone, he commercialized that to form a company called Atlantic Telephone and Telegraph, or Atlantic Telegraph and Telephone. AT&T became one of the biggest and most powerful companies in America. And of course, as they were developing phones, they ran into a lot of technical problems, and they built a lab very much modeled off of Edison's lab, where they would give smart people their problems that they were having, putting phones together, making them work, and then told them the problem, got out of the way, gave them some money. That was called Bell Labs. And if I could give one other lecture, Bell Labs is also a fascinating place. Prolific American invention lab, a partial list of what they invented, everything from the transistor that we're talking about today to the laser cellular networks, C programming language. We're talking about that. Just so many things came out of there, and so many smart people were there working as well. So again, these were all working on practical problems, but in the process of it, they produced 9 Nobel Prizes. Who knows what a Nobel Prize is? 4 Turing Awards, which is like a Nobel Prize for computer science, and 28,000 patents. So it's like a remarkable place that they put together to support problems with Bell Labs, to solve problems for AT&T. It brings us to the first hurdle, which was, I think I've got a picture in here somewhere. I talked a little bit earlier about vacuum tubes. And this was around the 40s. This was state of the art. These were used in radios. That gives you a sense of how big they are. And they were sort of the first switches. They were what you used instead of a transistor. Yeah, radios, computers, phones, vacuum tubes. Phones was the key thing because AT&T was really interested in making their phones better, and like long distance phone calls needed ways to amplify. But vacuum tubes were these big, they were hot, they were fragile, they burned out. I think I mentioned earlier that the first computer with them, ENIAC, it had 18,000 of these, and they broke every 2 hours or so. So you had to send people around to replace them. It was not a good solution. And that was the problem that Bell Labs was trying to solve, was what to replace the vacuum tube with. Enter our first character here, William Shockley. He was a complete genius, and he was quite a jerk to work with. I got offensive weirdo, and that probably describes him well. PhD at MIT, Bell Labs physicist, the 9 Nobel Prize winners. 1945, he sat down with some pen and paper, thought about this problem, and like drew out the solution, which was the theory of what a transistor would be. So he started out by drawing out the theory, and then over the course of 2 years, he and 3 other physicists at Bell Labs built a working transistor out of thin air. So new idea. Nobel Prize in 1956. It was kind of a big deal to the rest of the world. Sounds awesome, but he was described as obnoxious and arrogant. He tried to take credit for the entire invention, pushing out the other 3 co-inventors, a real jerk move. He had deeply troubling racist views and would stack rank races against each other, and eugenics, which was very taboo, very terrible thing to talk about, and even strongly opposed democracy. Like, he was kind of a bad person to hang out with. So that sort of brings us real quick to our first, got the invention of the transistor. Radios, computers, phones ran on them. They failed easily. Transistor miraculously solved a lot of these problems. That rarely failed, didn't generate as much heat, and it was not as fragile or as hard to produce. Miracle breakthrough. And I'll argue that that first hurdle, we would not have gotten that if it hadn't been for the American value of freedom of speech. In many ways, he was obnoxious and terrible to be around. He was still a brilliant physicist, and he added value to society. His ideas, good or bad, got a hearing, and that's American value there. And I'd say in a system where his ideas were blocked or where people tried to shut him down, they would shut down the bad ideas that were offensive, but they would also have shut down the good ideas, the transistor. And so he was an American, and they're inventing, and it was. And so Bell Labs patented that, and that was off to the race. Hurdle 1 on our way to mass PCs solved. And there's another great historical side note here. AT&T made this accidental gift to the world. Really poetically, the first thing that they invented, or the first thing they made with this, remember Alexander Graham Bell was obsessed with the deaf. They miniaturized hearing aids. So you can see in 1938, these things were as big as a backpack. They were terrible to carry around. And by 1953, with this transistor that miniaturized stuff, really tiny, like it's a huge human achievement to be able to do that. Those radios I mentioned, my grandfather had a box radio set that was like this big. And then suddenly in the 50s, we were able to produce transistor radios and long distance calls, which was what AT&T was trying to make money off of, right? Look how small the hearing aids get. AT&T was so big and powerful that it was considered a monopoly, and antitrust lawyers were after them. And their lawyers at AT&T said, we should patent this to everybody because we don't want to build a stronger case for us being a monopoly. So they bargain basement priced it at $25,000, and everybody could come in and license the transistor for a steal for a song. Texas Instruments licensed that, became a competitor to them. And Sony, everybody knows Sony Walkmans. They went and licensed it immediately and blew up all over the world. Hurdle 2 of 5, the tyranny of numbers. I promised I would explain what that is. But now we've got the transistor. It's pretty remarkable. William Shockley, distasteful genius, decides he wants to make a lot of money. He goes west and starts Shockley Transistor. He left Bell Labs, which was in New Jersey. He went all the way across the country to Palo Alto. Interestingly enough, Silicon Valley was started because William Shockley's mother lived there, and he wanted to start his company to live next door to his mother. That's right. Founded Shockley Semiconductor, where they're going to make transistors. Everybody was going to need a transistor. I'm making a lot of money. And he's a Nobel Prize winner, and he's got a great idea. It was easy for him to recruit the absolute top talent. All the great young engineers wanted to come work for him. He got them. It was easy. And he proceeded immediately to make their lives awful. He was a paranoid manager. He gave people, do you know what a polygraph or a lie detector test is? He would give his employees lie detector tests to make sure they weren't cheating or giving secrets to other companies. He was just really terrible. He would put people's salaries, what he was paying them, on a chalkboard and then rank them. A pretty awful place to work. So these guys, not as happy as they look, but these are some of the early 8 engineers that worked at Shockley's. But he was Shockley. He was a Nobel laureate. He had invented the transistor. He was kind of a big deal. The problem that they were trying to solve at the time was the tyranny of numbers, sort of the second barrier to getting to a general use purpose microchip. And that is, you got this is your first transistor invented. It's pretty wieldy. It's pretty big. And I remember when we talked about Boolean logic, you wanted to start to string as many of these together as possible, because the more you strung together, the more math you could do, the more logic you could do, the more valuable they got. Every component at the time had to be individually wired. And so as you put these together, you ran up against this increasing distance between them. You had wires going everywhere. There were failures. They were hard to assemble. And there was a lot of increased cost in terms of the size. So even though they managed to shrink it down pretty rapidly to this very small size, when you started to put them together on a board and put a lot of them together, this is like a terrible thing for somebody to have to try to manufacture and build. So as you try to make it more complex, got slower, got more painful to assemble and to operate. So the mission became, let's find a technical solution that will get as many of the transistors onto a single piece of material, so we're not doing this mess over here. Brings us to the traitorous 8. You remember those 8 unhappy fellows that were working for a god of semiconductors? Progress slowed, probably because they were taking a lot of polygraphs and because he was paranoid and he was making everybody upset. There's William Shockley looking stern. The 8 engineers decided they had enough. They asked him to leave and said, maybe you could just do something technical and not manage, or we could hire a manager. He said no, because he's Shockley. They bailed, all 8 of them. And you can see here, they're much more happy. Shockley referred to them as traitors, and they're known by history as the traitorous 8. But all 8 of them left, said, screw you, started a company down the street called Fairchild. We'll talk about it in a second. That brings us to our second American value, this irreverence. He was William Shockley. He was a big deal, right? But he was still painful enough to work with. These guys were like, look, we can do this a lot better if we just leave. So screw this guy. And I would say in many countries, there's a blind respect for hierarchy. Say like even a lot of European countries, they've got titles and you have to respect that. In America, there's this irreverence toward rank and status. It's very results driven. And if a guy is slowing you down, got to get rid of him. In this picture, interestingly enough, Robert Noyce, we'll talk about him in a second, but spoiler alert, he gets a Nobel Prize. Gordon Moore goes on to Moore's Law. You may have heard about how the speed of semiconductors will double every few years. And Eugene Kleiner went on to found Kleiner Perkins, which was the first venture capital firm. So these guys all went on to do really amazing stuff. But the first thing they did was found some Fairchild Semiconductor, which solved the tyranny of numbers. It's pretty rapidly, Robert Noyce solved the problem. Less polygraphs, less interrogation. They come up with this idea. And you can see this is what's called a monolith, but it's a plate saucer about this big. And it's the start of putting transistors, like putting them in a single layer on something about the size of a plate. We called it, this was the first integrated circuit. You could get more circuits in one place. You could get them to go faster calculations, solve this problem. Robert Noyce received a Nobel Prize for this. So invented that pretty rapidly. And then that solved the tyranny of numbers. So we went from that big chip down to just a saucer. But this is still a lot bigger than we know semiconductors. So we're going to go after small now. So the next hurdle was miniaturization. Jay Lathrop, scientist. So you mentioned the problem is still that ICs are big. We need to make them smaller. The state of the art now was to build this thing that's about the size of a plate. And to do that, you had to take beeswax and you'd spread it all over where the circuits are not. So you kind of like rub it all over here, and then you'd wash it with chemicals, and then it would eat away one layer and you're left with the conducting layer. And then you would do that a few different times, but you're very limited because you're working with, everybody knows what wax is, like beeswax or like candle wax. You're using that and you're using your fingers more or less. It was a very unwieldy system to actually make it. And it could only be made so big. So Jay was working on, he was an army researcher. He wanted to put fuses in the front of artillery shells, but he wanted them to be very small because you can't put a big plate on the front of them. And so is kind of a quirky guy. He started playing around with microscopes, turned one upside down, and very rapidly invented photolithography. So the idea was, rather than sort of smear wax all over and then run a chemical process over it, you make this thing labeled mask up here. It's very big. You draw your circuit, you run light through it, and then through a lens, and then down to the chip that etches the pattern, the pattern that we're looking for a circuit. And he did this by playing around, like I said, originally turning a microscope upside down, inventing photolithography. Somebody said ASML earlier. They're a very large company as well. That's all they do is they do photolithography, that one step. He patented it. He went to go work for TI, Texas Instrument. You can see here, I think Gordon Moore, Jack Kilby is holding up a mask. So that's it. You can kind of see what a circuit looks like there, but you shine light through that, down, focuses, burns in a new chip. American value, pragmatic, not dogmatic. Basically, he was laughed at because he took a microscope and turned it upside down. A microscope takes something small and then blows it big so you can see it. And he sort of had this idea, I want to take something big and make it very, very small. Yeah, and he played around with stuff till it worked. And when it worked, he moved on. You can see now we went from saucer size, you can see a coin here, right? About the size of a Tenga coin. And that's where we're at now. So we can really getting really, really small for what an integrated circuit looks like. And we'll use this process. So hurdle 3, miniaturization solved. Still have a few other things along the way, but like right after we invented the integrated circuit concept, 3 days later, the space race starts. So Sputnik, and for the Americans, this was a pretty scary moment because we suddenly thought, hey, the Russians are way ahead of us, motivated a lot of focus on science and technology and opened up some money. So NASA became Fairchild Semiconductor's biggest customer, buying chips, trying to go to the moon. And Cold War powered a lot of semiconductor development afterwards. So only a few days after, just kind of an ironic twist of fate there. Suddenly, the chip is not just for nerds and for the lab. It's actually got a lot of national security and it's starting to become that strategic piece that we were talking about in the beginning for countries. All right, hurdle 4 of 5 is repeatability. So now we're making chips, we're making them small, but where we run up against the next big problem that the industry still struggles with today, it's yield. So it's basically, we can make these small chips because they're small, little pieces of dust, little defects, little just about anything can get in the way of those beams of light and mess up the chip. So when you make 100 chips, we call the yield, it's like how many chips you get out of that. Only 1% works. So you would sit down, have a guy make 100 chips, one would work, and that was probably good enough for what you needed to do. But it really was a economic hurdle because it made it expensive. If you're going to build something to go to the moon, you can afford to buy a chip and have 99 of them fail, but you can't make computers and you can't make phones with that kind of output. And so this brings us to Morris Chang, another super fascinating person on this 5-person journey. Morris Chang was born in China, fled China for Hong Kong when the Japanese invaded in World War II. And then he fled Hong Kong for China when the Japanese invaded Hong Kong. And then he fled China to go back to Hong Kong when Mao Zedong took over. He had gray hair. Did everybody see his hair there blowing in the wind? I should have made this bigger. Okay. He's a super brilliant guy. Got a full scholarship to Harvard. Left Harvard, dropped out to go to MIT because it was a better engineering school, got a Bachelor of Science, a Master's in Engineering and Master of Science, went to Stanford, got his PhD, and then went to Texas Instruments in 1958. Texas Instruments, semiconductor company in Texas. Everybody knows that's the South part of America, deep South. And this was right in the middle of our civil rights era, which was kind of a time we were talking a lot about race. And we're talking a lot about equality. Texas was a hard place. If you did not look white, it was not an easy place to live. He was brave enough to go. He didn't know anybody there. He went down there, looked different than other Texans. You can see Morris there getting one of many awards among his fellow Texas Instrument guys, but he went there and he performed, rose to the ranks, and very quickly, TI realized how smart he was and put him in charge of all of their integrated circuit manufacturing. TI had a problem. When they made chips, they made that 1% to 2% yield, which was just super expensive. And they realized that if they kept going at 1%, they just would not have a business. Basically go into the factory, write everything down as a recipe. He would tweak a few small things. You got chemicals and pressures. You have the time that you sort of do things to the semiconductor. He would write that all down and then tell them what to iterate. So here's him in the factory telling a guy, looking at some data. They'd go back and do it again. He's just a calm, focused guy who took his data. TI put him in charge of all the manufacturing of all their integrated circuits. And in the matter of about a year or so, he drove through systematically looking at this from 1% to 25%, which was kind of a miracle because it meant that rather than 1 out of 100, 25 out of 100 were working, right? And TI had a business. Morris Chang solved the problem. In the process now, actually a whole field in semiconductors is process engineering, where that's all people do all day is make minor tweaks to that process. I like the story of Morris Chang because it sort of illustrates meritocracy. He didn't look like he was from Texas, but he was just really good at what he did. He probably could not have risen like that, certainly not in China because his politics weren't right. He could not have done it in Japan or Europe because in those places, generally you have to look like you're Japanese or European to work there. It could only have happened in America. So he did it in America. And as a side note, Morris Chang worked for TI until the 80s. And then in 1987, he went to Taiwan and founded what's TSMC. The most advanced chips are made at TSMC. It's a strategic asset that you're talking about. Founded that in 1987. Morris did not get the Nobel Prize, but he's worth about $7 billion now. So he did okay. Last hurdle. Everybody ready? Got like cheap. We can make them small, cheap, reliable, but we need to make a lot of them now, right? All right. So last character here, Andy Grove. Andy Grove, he was born a Hungarian Jew. He spent the 90s in Hungary, dodging the Nazis. That was a tough time to be a Jew. And then in the 50s, when the Soviets rolled in, there was the Hungarian Revolution. He was on the wrong side of that. And so he fled and arrived in America, where he got his PhD in chemical engineering and joined Fairchild. So he was not with the original guys, but joined Fairchild and worked on process engineering, that thing that Morris Chang kind of single-handedly invented. When Gordon Moore, founder of Moore's Law, and Robert Noyce, that guy that got a Nobel Prize, when they left to start a new company, called them, Andy, I'm in. He went with them. They hired Andy Grove as like their first or second hire, I believe. And the company was Intel. So everybody kind of knows Intel inside. There's a handsome guy in the orange pants over there on the left is Andy. It's a more mature Andy later on down there in the black and white. And the Intel, like the most customers for semiconductors at that point were military space, big businesses doing big things. They had customers that had a lot of money. And Andy's insight was, as he climbed the ranks, was if we made chips these reliable and ubiquitous enough for consumers, then we would have this huge market and we would change the world. And that was considered heresy because these guys, the military space and big businesses, they paid so much for semiconductors, sort of a revolutionary thought at the time. And Andy just drove through good management and by finding intelligent people, similar to what Fairchild and what Bell Labs and what Edison did before, they turned this into the PC revolution, where we now have reliable, cheap, fast enough semiconductors to do just about everything that we do on Earth now. The American value here, I think this illustrates, is that outsiders are welcome. Andy Grove was definitely an outsider, spoke with an accent and came from Hungary, but he was thinking differently and he was rewarded for it. And, because of him, everybody can buy chips and the consumer era begins. So, all right. So we have gone through small, cheap, and reliable, sort of when I call it the American gift to the world. Even though America invented it, it quickly became global. And I love this diagram. This is from the Computer History Museum. Fairchild's in the center. These are all the companies that people left Fairchild to go found and start. I can't see it very well, I guess, but most of Silicon Valley can find its like heritage back to Fairchild Semiconductor. But it also quickly became a global story where very quickly you saw Sony was one of the first to license the semiconductor. Japan started getting in on manufacturing. Hong Kong became a manufacturing epicenter. Singapore became a manufacturing for the precision and affordable manufacturing labor until this, Morris Chang left to found TSMC, the most important companies in the world now. And we're to this point today where the idea of semiconductors is spread all over the world. When you make a chip, it'll sometimes travel 10 times around the world before it goes from design to final consumer. Everybody participates. even, interesting enough, Kazakhstan. So a few weeks ago, I had the pleasure of interviewing one of the person who designed the first semiconductor in Kazakhstan, Professor Nursultan Kabilgas. He's a professor at Nursultan University, and he led a team to design first semiconductor in Kazakhstan. So I would encourage you to go Economist and give it a listen. But I think it goes to show just how far everybody can participate and how important it is to every country to be able to participate in all the things that are semiconductors. In recap, 5 technical hurdles were 1, 2, 3, 4, 5, everything from shoddy logic all the way up to scale. Can only happen in America, not because Americans are smarter, but because of the some of these 5 American values that we talked about that made it possible. Shockley, Noyce, Lathrop, Chang, and Grove all represent them. And that's pretty much it. That's the story. You can reach me. I'd love to connect with you on LinkedIn, send me a LinkedIn connection, or connect with me on the Siliconomist and listen to more nerdy stuff about semiconductors. Thank you. All right. That's all I got. Yeah.
Taken over. The largest in terms of scale of production is Taiwan.
Yeah.
Probably this is an area of interest among USA and China.
That's exactly right. Yeah. So over the last 30 years or so, Taiwan has built up. TSMC has become the most cutting edge chips are made there. So I think that the only supplier right now that can do Apple chips like for your iPhone and that sort of level of chip. The challenge there is that China believes that Taiwan is actually part of China and makes threatening moves to come back and make sure that Taiwan knows it's part of China. Taiwan says it's not part of China. And the rest of the world does not want that to happen, because when you control supply within your borders, you can also, not only do you choose who gets to buy semiconductors, you've seen that where the US has told China now you can't buy our newest or best semiconductors, but you also can put, you control supply chain, you have the opportunity to put back doors in. So if you roll back even say 7 or 8 years ago, Huawei was banned from selling in the US because the US was concerned that there were backdoors in all of their chips to go back to China, meaning that they left some encrypted way in. It's a very big national security threat, not just from like, I want my missiles to always be my missiles and to work whenever I need them to work, but also I don't want anybody to be able to turn off my water or my power. Think of all the places that those semiconductors go if somebody can get into them. So that is like absolutely a very big concern right now. Yeah, that Taiwan controls that. There it was interesting. So I got my start in semiconductors working on the CHIPS Act, which was the US's like reawakening to just how much we had lost in terms of semiconductors. Part of that deal was they convinced TSMC to start building factories in Arizona. So there's an effort now to realize we need to have some of that back inside the US, like all parts of it. But when you think about like a semiconductor really does